Okay, so in this video we're going to talk a bit about testing of theories. So, as I said in the theory construction video, good theories are ones which have been developed with strong derivation chains. Strong derivation chains ensure that theories make specific predictions, which mean that they're ready to be tested. So, for example, a good theory will make what's known as a risky prediction. Importantly, it tells us what we should not observe if the theory were true. This means that our theory is able to be falsified easily through experimental tests if it indeed is not true. Now, Paul Meehl was a philosopher of science and a clinical psychologist who wrote heavily about this, and he has a very interesting paper about the appraisal and amendment of theories from the perspective of Popperian falsification, with some subtle amendments based on his on Popper's student Imre Lakatosh's work. And Paul Meehl uses this term that he refers to as the Spielraum, which essentially is a German word which means kind of range of play or space of play or field of play. And he says that good theories are theories that specifically designate what their Spielraum is. And what that means is they designate the range over which we should expect to see certain values of observations that our theory makes predictions about if the theory were indeed true. Now, much of the research that you will encounter out there in the world of sports therapy, exercise, health science, and so on and so forth make what are known as weak predictions, or flabby predictions, as Meehl would use in terms of his terminology. Most of these studies start with what is called the assumption of the null hypothesis. So they start with the assumption that there is no difference between, for example, two interventions, rather than starting with the prediction that, based on theory, intervention A should be X amount better than intervention B. And the reason that the null hypothesis is so weak in terms of testing theories is that it's very easy to reject it. So the null hypothesis essentially states that we should observe that if the null hypothesis is true, that there should be no difference between two interventions. What we really want, though, are theories that make predictions that, at minimum, are directional. So, for example, on the left-hand side here, a theory that made a directional prediction would say that, for example, we should see only values that are positive or only values that are negative, depending upon what we're interested in. So this theory that makes a directional prediction as to which would be better or which would be higher comparing two different values, or if there's some sort of parameter that we're interested in, it would exclude a certain range of values below a particular value or above a particular value, but would include those on the other side. These are what are called directional predictions, and as you can see, the theory tells us that there's a certain range that we should not see. And so if we conducted an experiment and we observed values that were in the range that the theory did not predict, then we would be able to say that our theory is likely false. Now, we can make our predictions stronger and stronger. So, for example, we could specify an upper and a lower range. We could have a range of values throughout which we would expect our theory, we would be able to observe predictions if our theory were true. We can tighten this up and we can make smaller predictions, and the strongest of theories make what are known as point predictions. They'll predict precisely what we should observe out there in the empirical world of the phenomena that we're interested in. Now, another thing that theories can do is also make predictions about the relationships and the functional forms of relationships that we might observe. So, for example, if you're interested in therapeutic interventions, you might be interested in the manipulation of the dose of a particular intervention. And so you might be interested in how much of a dose produces how much of an effect on some outcome of interest. So, for example, these three figures here, you could imagine on the x-axis at the bottom you have the dose of the particular intervention, and on the y-axis you have some outcome measure of interest. And so you may have a theory that predicts a linear response between dose and outcome. The more of the dose you give, the higher the outcome. Or you might have some theory that predicts that there is some threshold phenomena where up to a certain point outcomes improve, but after that point you just see a plateauing of effect. Or it might be some quadratic function where up to a certain point it improves, but after that taking too much of the intervention actually starts to reduce the effectiveness of it. So theories that make strong predictions like these are good theories because the predictions are risky, and we can design studies that test to see whether or not we can falsify the predictions that the theory makes. Now, one thing we need to be clear of here, and this is an important point that Lakatos and Meehl make with regards to Popper's strong stance on falsification, which is to say a single observation falsifies the theory, is that in reality what we end up doing is actually testing the conjunction of the theory with a number of other assumptions. So, this diagram here refers to the state of kind of play with respect to what we're trying to do in research. We may develop some kind of substantive theory, and that substantive theory may lead to some kind of statistical hypothesis that we test. The reason we end up with a statistical hypothesis is that we often have to rely on taking samples of people from a population of interest. We'll discuss this more when we cover statistical inference in a later week. But needless to say, we're very rarely able to do a study where we can test every single person in the population of interest that our substantive theory refers to. Now, the inferences that we make from the statistical hypotheses that we test to the theory are what's called the corroboration problem, or the problem that the theorist has. The inferential statistics problem here on the other side, as I said, is something that we'll deal with when we get to statistical inference later. But for the moment, from the statistical hypotheses that we test, which are based on the observations we make, we have some conjunction, which is not necessarily the theory in and of itself alone. So what we have is we have this conjunction P, which consists of the theory that we're interested in testing, but it also consists of a number of other factors. So we have what's known as our auxiliary theories. I mentioned this in the previous lecture about theory construction, that sometimes we have other theories that we utilise in the development of our theory of interest. And so we have to take these into account as well. We also have what's known as the ceteris paribus clause, which is just a Latin phrase for saying all other things being equal. We also may have some auxiliaries about our instrumental instruments that we use. So for example, if we're testing our theory, making observations using a particular kind of measurement device, we also have to include assumptions about the validity of that measurement device, the reliability of that measurement device. And then we also have the other particulars, Cn, of the experimental situation itself and the assumptions we make about whether or not our experimental manipulations work, or whether or not we were able to sample the participants as we liked. So if we go back to our kind of modus tollens approach, which was the idea that as Popper suggested, what we want to do is falsify theories where, for example, if the theory P is true, then we would deductively observe Q, and if we don't observe Q, then we can say our theory is not true. The reality is it's not the theory T that we can falsify here, but it's the conjunction of all of these things. So for example, where Q is some deductively entailed observation from P, which is the conjunction of our theory and all of our other assumptions, then if we observe, or if that conjunction P is all true, then we should observe Q. If we don't observe Q, then we say therefore not P. But what we actually end up being able to do is not necessarily having to reject the theory outright. We can start to question whether or not maybe some of our assumptions about other theories were true, or auxiliary hypothesis, whether the ceteris paribus clause was incorrect, or whether there were issues with our instruments that we used, or whether there are other particulars of the experiment that might have led to us not observing what we think we should observe, given that conjunction which includes the theory. So Meehl takes and Lakatos took a slightly softer approach, which says that what we do is we tend to engage or expose our theories with this conjunction to varying tests. The more tests our theories survive, the more money in the bank it has, the higher verisimilitude it has. But if a theory fails a test, we don't necessarily throw it out straight away. We think about whether or not we can question some of these other assumptions and strengthen it up a little bit. We go back to the derivation chain we discussed in theory construction, and we think about whether or not we can strengthen that derivation chain such that future tests of that conjunction might be better tests of the strength of the theory itself.